Hi, I'm Philip.
I'm Bella,
Hello, my name is Kieran.
and today we're going to be reviewing the 2025 paper by Dr. Sean Bauer and colleagues titled Defect Sensitivity of High-Strength Steel 42CrMO4, where they investigated critical gray area in fatigue failure. A range of defects are added onto quenched and tempered 42CrMO4 steel alloy, and the sensitivity of the material to the defects was tested to find its fatigue limit. This material is valued in machines due to its high strength and toughness, and it's used in including, but not limited to, automotive parts, heavy machinery, and aerospace components. So their core research question is, at what point does a defect stop behaving like a geometric notch, where we worry about cracks starting, and starts behaving like a crack, where the crack exists but might stop growing? Being able to determine the fatigue limit mechanism is important for the safe and smooth operation of these various machine components.
So I'm going to go over some of the vocabulary and nomenclature. A fatigue limit is the stress level below which a material can withstand a theoretically infinite number of loading cycles without causing fatigue. Steel, for example, would have no fatigue limit, and aluminium, for example, would have a fatigue limit. A notch root radius is the radius of a curvature at the bottom of a notch in a material or component. A low radius is a sharper crack, and a high radius is a more rounded out. S and N curves plots the stress amplitude defined as S against the number of cycles defined as N to failure for a material subjected to cyclic loading. Propagation, the process by which cracks grow in materials due to stress and strain. And defect sensitivity, the ability of a system to detect defects in a material or process.
So a little bit about the experimental design. So defects are imperfections in material, but not all defects are cracks, and they don't always behave in the same way. So while some defects can determine if a crack starts, some affect whether a pre-existing crack can continue to grow. So to simulate defects, they intentionally drilled holes ranging from 50 microns, about the width of a human hair, up to 1,000 microns. They subjected these samples to ultrasonic fatigue testing, which vibrates the sample at 90,000 hertz, allowing them to reach over 1 billion cycles very quickly to find the exact fatigue limit where round secured. They then used a technique called scanning electron microscopy to look inside the holes of the samples that didn't fail to see if tiny cracks had started but stopped.
So for their findings, they found that for very sharp, small defects, the fatigue limit wasn't defined by whether a crack could start, but whether it could keep going. In this zone, they found what they called non-propagating cracks, which are cracks initiated but didn't form further. However, for blunt defects, larger holes, if a crack started, it always led to failure. These were non-propagating cracks.
And
There were no non-propagating cracks.
And they basically use this information to define a critical notch root radius of approximately 80 microns for this specific steel alloy. So below 80 microns, the defect acts like a crack, and above 80 microns, the defect acts like a notch. A model can be used to predict the behavior of defects. So if you use the wrong model for the wrong size, you will basically miscalculate the safety of the entire material, which is very fascinating.
So a little commentary. An interesting insight from this paper was a specific detail about where the cracks formed. So cracks typically initiate where stress is concentrated, which in theory should be the equator of the hole. But looking at the FEM data and the samples, the cracks started at the corner of the hole. This highlights a gap between textbook theory and reality, and suggests that surface finish and drum techniques matter just as much as the hole size. Additionally, we wonder if the critical radius of 80 microns changes if the grain size of the steel changes. If larger grains shift this critical value, it is just another important variable for manufacturing quality control.
This paper answers the core question by defining a notch root radius, where you have to use different models to predict the different behavior of defects at a critical point. Thank you for listening.